pleasure to introduce my collaborator, not on this project, but on other projects. Actually, I would say my favorite grad student who doesn't work for me, Nhung Nguyen.
Thank you very much.
Great.
Thank you Ken, for nice introductions. My name is Nhung Nguyen. I'm from a Lincoln Lab, Norbert Lincoln Lab at the University of Maryland. And today I'm going to talk about our results on the simulation of the Lattice Schwinger model on a trap ion quantum computer. In the context of this AQS meeting, and also our final goal is to do simulations of quantum systems. And we know that classical simulation of quantum system is hard, as we learned from the summer school lectures. So Feynman said, maybe we can use a quantum system to simulate a quantum system. It's turned out that well, this can be done efficiently, as we learned from the summer school lecture. And so what are the requirements for those quantum systems that to be used as quantum simulator? They need to be well controlled and well understood. There's a few examples of these quantum simulators that we have been seen in the talk so far, which are superconducting qubits, like Dominic talked, or color center and quantum dots, and some you hear work on that, and or photons in cavities, or neutron atoms in optical lattices, or Rydberg atom in the tweezer arrays, which what Matt Safman talked about in the summer school lectures, and polar molecules, and trap ion, which is the focus of my work and many people at the Duke Quantum Center. So that's what I'm going to talk about. So why ions? Well, they are the perfect qubits because they are well isolated and they are identical, which means they have very long coherence time, and they are well controlled and read out with high fidelity by laser or microwave field. And important things about ions is that they have charges, which allows them to be trapped and interact and control. And these motions that induced by these F-trap fields and Coulomb interactions, they can be used to mediate the entanglement between any subsets of ions interchange. So we will focus on that later. So the outline of my talk is like this. The first part, I'm going to talk about our experimental setup and how we do gates. And the second part, we'll talk about how we'll implement this using our setup to perform the simulation of the Schwinger model. Okay, so we, as many Chris, disciples, are using Ytterbium 171. This is the electronic structures of Ytterbium 171. It looks very complicated, but don't worry. We mostly focus in this hyperfine ground state level here, which we use as our qubit. Why? Because they are very magnetic field insensitive to the first order, and with this we have achieved long coherence time of 1.5 seconds in our lab, and many other people have achieved even longer coherence time of like an hour. Well, this is the T2 coherent time. We don't have T1 because this is hyperfine qubit. So, and we take advantage of this dipole Lau transition to do cooling, Doppler cooling, state initialization to this zero stage by optical pumping and state detections by fluorescence between 1 and this upper state. Okay, I'm a bit nervous, so this one goes like crazy. Yeah. So this is the schematic diagram of our setup, and so this is our linear chain of trap ions where we trap with the AF power trap. And we collect these fluorescent light, detection light by this optics, high NA optics here, and we image them in a multi-channel photo multiplier tube over here. And with this, it gives us very high detection fidelity. This is the PMT array, the image of the ion, and this is the camera image. And with this, to control the ions, we use a pair of counter-propagating Raman beams with one of them is split into individual beam, and the other one just address all the ions in the chain. And so these Raman beams would coherently drive the qubit state from 0 to 1 via 2-photon transition to this virtual state here. And the reason we choose this state is to minimize the 2-photon stack shift for this transition. And so with this, we can drive our qubit very coherent, and we can address any qubits in the change by turning on and off this AOM channel using our AF signals. So we have like individually control. And the reason why we use the Raman beam is because we want to excite the ion motions, which will be strongly excited by a laser beam, which it gives you a very strong momentum kicks. Yeah. So with this Raman beams, we can perform very good single qubit rotations around any axis on the along the equatorial plane. So by shining the laser beam on one of the ion, and by tuning the durations of the beam of the pulse, you can apply different angle of rotation. And by changing the phase of the pulse, the laser pulse, you can change the phase, which means the axis of rotation. And this allows us to implement this unitary evolution with high fidelity. So theta is the durations of the laser pulse, and phi is the phase. So for the 2-qubit operations, we use the ion motions, as I mentioned before. So the idea here is that you would do a spin motion entanglement, and then because the motions of the chains are shared, you can use that to entangle the the two spin. So the motion acts as like an information bus to allow entanglement between the two spin. And so here is the chains of 5 ions. You can see that they have different modes of motions. So 5 ions mean there's 5 different modes for each direction, X, Y, Z. So in our experiment, we mainly focus on the X direction where our laser beam couples strongly to. So if you look on the frequency space, okay, so here we call it circular transition, and this is the qubit frequency. This is like you just tune the laser to your qubit splitting, which in our case like 12.6 gigahertz. And then if you detune your laser, which you change your laser frequency to either like higher frequency, or we call it blue or red, which means lower frequency, then you can excite these sidebands. So what are these sidebands? They are corresponding to the ions motions. So if you detune them here, you're driving a blue sideband, meaning you excite a qubit and increase one quantum motions. If you detune them here, you would excite a qubit, but de-excite one quantum motions. So you kind of like cool them down. So to drive a 2-qubit operations between any ions, what we do is we perform we sight a two-tone or two-frequency laser pulse that are symmetrically detuned around this carrier frequency. So they have the same intensity but opposite detuning. And this allows us to perform these unitary operations, which entangle the ion internal degree of freedom, which is the spin that we use as a qubit, to the motions of the ion chain, which is the center of mass of the ions, and which described by this term here, which if you're familiar with, is a displacement operator, and it, through this ion motion, because it's shared, it also induces a spin-spin entanglement, spin-spin coupling between the ions. And if you carefully control the laser pulse, what it means, there's like a whole topics or a whole field of research focused on doing this. And you do it very well, you cancel this spin motions entanglement, and you're left with just the spin-spin entanglement. So you're only left with the Ising coupling, and now you have, you start from 0, 0, you have a maximum entangled state. And you can construct the C0 gate from these, we call this XX gate or Marmon-Sorensen gate, if some of you may know. It's with we form the C0 with the single qubit notation and these XX gate. So with this, I show you, with our qubit Ethernet 171s and the optical addressing that allows and by performing pulse shaping, we can do like these XX and add rotations that allow us to do C0 header map and C phase gate, control phase gate, which allow us, to do different algorithms. So we have been performing many algorithms over the years, some of it with my involvement, some of it happened before me. So, this is a non-exhausted list. I think it's been done in my lab, in Naba's lab. Yeah. So this, if you want to check out more stuff, look at this link. Well, so cool. We got our, programmable quantum computers, simulators, and with 9 qubits. So now what do we do with it? So, a lot of things. But here I'm focused on this simulation of the Schwinger model. So why do we want to simulate the Schwinger model? First, what is the Schwinger model? It's the quantum electrodynamic in one space and one time dimension. And quantum electrodynamic is like a gauge theory, and gauge theory, like QCD, quantum chromodynamic, and other big stuff. They describe fundamental forces of nature and simulating gauge theory, which can be written as K local Hamiltonian. Okay, now I can use this term because it's introduced in your lectures, summer school lectures. It's efficient, as Andrew John has shown. And well, that's a good news. So we can start simulating this gauge theory. And our Schwinger model is the simplest one of them. I think so. Yeah. And but still very interesting because they have some quantum chromodynamic light phenomena, like they allow you to describe hair creation and annihilation or string breaking dynamics, which a lot of people care about. So they've been used as testbed for quantum simulation methods by a lot of groups here. So we're not the first, but we hope to, do some long-ish digital simulation with our experiment. So, okay, first, you got like a spin system of your quantum computer. How do you simulate this abstract gauge theory, which are like continuous model of fermion and bosons? So, first, you got to discretize the space and time. So here we discrete discretize the space, and then we would use the Hamiltonian evolution to evolve time. So you put the fermion on the lattices. So fermion here and anti-fermion here, and then the link between them at a gauge degree of freedom, which at a boson are in these operators. Okay, wait. Yes. Then you map the fermions to the spins, which will tell you how to do that later, but I guess many of you here already know. And you also map the boson to the spins, either by truncation or by some clever mapping to the fermions, and then to the spin, or some other way. Well, and then you convert to your native gauge set, and then you, which sometimes look like this, and then you do it. Yeah, so how do we apply that procedure to the Schwinger model? We use the Koga-Sky formulation. So now, you know, the oxide would be a positron, and the even side electron, which is fermion. The other one is anti-fermion. And the link between them is the electric field, because this is one space dimension. So luckily we can forget about the magnetic field. And so we have this Hamiltonian, which have three terms. The first one, which is the kinetic term, which describe the interaction between the bosons and the fermion, like hopping. And then the second term describe the energy of the fermion, and the third term describe the energy of the bosons. So they need to obey their respective commutation relations. More important thing is that, well, guess what? Because this this is QED, so the physical state of this Hamiltonian must obey charge conservation. So you look at the volume here, the field, integral over the surface have to be equal to the charge inside. And which means that if you look at this line here, you make a box like this, the field to the left minus the field to the right must be equal to the charge density, which if you write like a Gauss operator like this field to the left minus the right equal to the charge density. Yeah. You require that your physical state must be in this zero Gauss charge subspace. This would come in handy later. Well, yeah. So, well, how do we map the Schwinger model to the spin? As I said, you use Chapter and Wigner to map the fermion to the spin. I think many of you are familiar with this. So now spin up would mean no positron for the oxide, and down mean there's a positron for the oxide, and for the even side is the other way around. So up means there's electron, and down means there's no electron. And so now your Hamiltonian become like this. All the C or psi plus would become sigma. Then you left with this U and this E. And then for the bosons, so the first way is to truncate the levels, because the boson is infinite level operators. So you you have to cut it off somewhere, because you don't have infinite number of qubits. At least we don't. And so we cut it off to 2 lambda levels. So, and we set the conditions so that the raising or low, I think is raising operator, yes. Raising operator, so for the highest level, go to the lowest one. And it means that for one boson, which is one link, you need about log 2 of 2 lambda spin to equal 2 lambda. And some people figure out that if 2 lambda is equal to n, which is n is the number of psi in your system, which is number of fermions, then this truncation have minimal errors. All right, yeah. So, but the other way to do it, as I mentioned, is do some clever tricks. So first we observe that these U dagger operators can be transformed away. So now you have only this E operator left, and we observe that by using Gauss law, you can rewrite the electric field to the right equal to electric field to the left plus the charge density, which is the fermion field. And by recursive relations, you can rewrite all the electric field terms as the sum of all the charge density, and by setting the leftmost electric field to 0, which is the background, you got this sum of fermion terms here. So now you kind of map your boson interactions into a string or long-range interactions between the spin. And that means that, well, how do these two formulations compare? Well, obviously, for the fermion boson simulation, you need a number qubit for the fermions and n times log 2 of n for the bosons, because each of them need log 10 of n. So there's n of them, mean n times of them. And the number of gates is found out in this paper by Alex Shaw. You need like about n to the 4. So we want to focus on this purely fermionic formulation, because we have trapped ions, so we don't have that many number of qubits. Okay, at least on our system. Other people have more. And we have all-to-all interaction, so that's not a big deal to us. Yeah. So we have less number of qubits, and for the number of gates, we do some calculation using like the commutator belt with just the triangle inequality and so on. You got this n to the 6.2. This is what you kind of expect, because you have this long range interaction, and you add n squared number of gates into them, and then if you use Andrew Chai's theory of Trotter errors, you kind of cut it down to a little bit. You have a tidal belt, and then we do a numeric on a small number of qubits up to I think 8 or 12, I forgot, which is about n 4.2. So it kind of close to this belt, which means it's a good belt. And so these two seem to be comparable, but here they're just doing a very loose belt. So maybe they're also doing much better in practice. Well, so we would use the fermionic belt, and purely fermionic formulation. So, and with that, now we have a spin Hamiltonian. How do we simulate it? So, well, as you all know, you gotta break them down to, many 2-qubit gates and single qubit gate, or 3-qubit gate if you have them. Instead of this like many qubit Hamiltonian, and then you have to discretize the time, because we don't have infinite time. I mean, or continuous. If you do it small enough, it becomes continuous. And so we do this using the product formula, like Andrew Chai talked about. So in the experiment, we use the first order product formula. Okay, you may laugh, but this because we have noise, and it's we did some numerics, and it turned out for second order formula for us isn't that better than the first order or the product formula. But for the gates just now analysis, we did with the second order. So okay, good. But not so good. So there's a caveat, like we have so many terms. How do we order them? It turns out it's very important that you have to order them correctly because the error scale is the commutators between the terms. So in this Chapter order theory, Chapterization paper, they look at these Heisenberg nearest neighbor Hamiltonian, where they have all this X, Y, Z nearest neighbor interaction. And if you order them like this, like all the X term or Y term or ZZ term or versus if you or you can order them like this with all the leading order term in support on the outside first, and then all the X, Y, Z of this 1, 2, 3, 4, and then all the even leading order term, which means the support is on the even one first. So like 2, 3, or like 4, 5. Then you can have quite different result. It's turned out from this paper that these odd even or even odd orders perform a little bit better. This is number of step if you require the same error accuracy epsilon, and the odd even order give you need or requires fewer Chapter steps to perform to the same accuracy for a different number of sides. Okay, so our Hamiltonian is not exactly nearest neighbor Heisenberg. We have some long range term there. So maybe, but well, we should try it out, see how it goes. I do some numerics, and well, this is a very big Chapter step or compared to what they do in the paper. And we'll see that of the blue points are the odd even orders, and they look pretty close to the blue lines, which are the exact diagonalization, which are a bit better than the red diamond. Yeah, so you gotta be careful in choosing your orders. Okay, so now we know how to order our Hamiltonian, how to do it with our native base. So we're going to do it. First, we got to choose the ground state. So we choose it in the ground state of this Hamiltonian when x equal to 0, which gives you the bare vacuum, which in a qubit language is like 0, 1, 0, 1, 0. And then we turn on the interaction, which means x is non-zero, and you multiply t. And then, which means you apply this block many times. And then you measure. Okay, we measure. And we measure the vacuum survival probability and particle number density and electric field density. So these three observables, they are closely related. So here I'm just going to talk about the first one because, if your vacuum type disappears, it means you have more particle, which your electric field density will going to increase, and so on. So, let's look at the experimental data. This is for 2 qubit, mean 2 sides, 1 fermion and 1 electrons. Sorry, 1 positron and 1 electrons. So this plot showing the vacuum survival probability over time. And you can see that this experimental point and the orange point, which show the oscillation of the vacuum over time. You can see here the vacuum is got destroyed, particle are created, and here particle are destroyed, annihilated, and you got back the vacuum, and so on and so forth. So you can see that the oscillation are dampened, which are because of error in the experimental system. The gauge error. And so we observed that when these errors happen, the Gauss law are violated, which means that now you look at the charge of the state, the charge density of the state, you start from the vacuum state, but now you have 1 positron or 1 electron. So, well, that's not possible. So what we do is we just throw them away and renormalize the state. So that's how we get the green curve points. And that means that they agree better. And this process we call selection. Okay, all well and good for 2 qubit. Now let's go to 4 qubit. Yeah, that's how many gates, 2 qubit gate. We don't count as single qubit because they are relatively cheap in our system. For 4 qubit, it's just 2 positron and 2 electrons. You can observe, this is the picture of the vacuum survivability over time again. And we choose this huge, big Jota step because we want to see long evolutions. So you can see here the experimenter kind of dampened, but the post-selection recovered pretty well. Okay, let's go to 6 qubit, 3 positron, 3 electrons. Okay, so now it doesn't look very good. You can see some oscillation in the orange point, but for the green point, okay, sorry, the other way around. Once you after post-selection, you see more oscillation than this raw data. So why? Well, because as I told you before, the number of gates doesn't scale favorably with n. So by n equal to 6, you already have like 22 qubit gates and this many single qubit gates. So by this point, we got about 80. If we go to here, we got like 100, which our gauge error is like about 98.5% average. So by this point, we have almost completely decoherent data. So I took this data point, but I don't think I should even show it. But it's like there's no point going longer. So what can we do about this? Well, there's some smart idea out there about how to reduce this errors, either Jota errors or experimental errors. So I'm going to tell you about one of them. So if we do Jota-wise evolution like this, then the Jota errors from each Jota step going to kind of add up. But say if we insert in between each step unitary evolution that commute with the symmetry of the Hamiltonian, then by the end of the Jota step, or of many Jota steps, these things are cut cancel out, like the Jota errors between steps and cut cancel out. The important thing is that the symmetry, the error doesn't commute with the symmetry, so that's why they got canceled out. While your Hamiltonian evolution, they commute with the symmetry, so they're left unaffected. So people who propose this, they are in a QUICS UMD center, in UMD, and they do some numerics and found out that if you apply this for these Schwinger model, different kind of Schwinger model, the first formulation, Mozart formulation, and they find out the leakage to the Gauss law violating subspace is reduced by 3 order of magnitude. Yeah, if they apply this unitary insert random unitary, which is pretty good, and they also apply this for some 1/f noise with a different correlation length, and they find that if the errors are correlated, then the reductions in these leakage errors is much better than say they're not correlated at all. So, well, it's worth a try. Yes, here is the experiment data. So the first plot showing the leakage to the Gauss law violating subspace over time. The orange part are the one with down symmetry protection, and the blue stars are the one with symmetry protection. Well, they perform a little bit better, but not that much, not significantly. And the green points are the post-selection. So by definition, they are very good. So what does it tell us? It tells us that the error in our system are correlated. And uncorrelated. Yeah. And the lower plot show you the total errors over time, and you can see that these random unitary, they does help a little bit, but not significantly, while the post selection is will improve things a lot. Well, yeah. So what next? What time to try out different error mitigation method. One of them maybe for the uncorrelated errors. So there's this paper by Hashim and others that look at this for superconducting circuits where they try to characterize their noise channel and do some random characterizations of the noise channel and apply some polytolling. So they apply it on the IBM machine and they recover the dynamics when they do the 2D easy model pretty well. So maybe we can try this on our trap and system. Or the second way is that, okay, so this thing doesn't scale very well. Maybe we should think of another way, anything else in our experimental system that can help with the scaling. So there's this phonon modes that I mentioned before that we don't use. So we're thinking maybe we can use it to encode the boson degree of freedom. So there's this paper by Naubert, my advisor, and Zore and Guido, who's expand on this idea for the Schwinger model and also the Yukawa model. So the idea is that now you have the spin that the fermion is encoded in the spin, and in the boson you can encode in the phonon. And you can do phonon gauge to simulate the dynamic of the bosons. So there's some technical difficulty when you engineer this kind of phonon coupling. So we instead of looking at the Schwinger model, well, basically you need to add another set of laser. That's always mean more difficulty. And we look at the Yukawa model first and see how it goes. Hopefully it goes well. And or you can actually build a better experiment. So I haven't tell you the dirty secret behind the experiment, but our trap actually have a lot more heating than it should be, and the phonon modes are very susceptible to heating, so we want to control that, better get a clean trap. And something that more closely to the ideal model. So we're doing that. We build a 3D monolithic trap, and that experiment is now moved here to do quantum center. But there's nothing. They're still doing it. So there's nothing to see yet. But well, hopefully it would be come into fruition in the coming years. So these I want to thank my collaborators, Zora and Mins, the theory collaborator, and my lab mates, the one involved and the one who's involved in this experiment. And thank you for the funding agency. So now I can take my question if there's time.
One thing you might want to look at as you find the number of your input parameters increases, you do something like genetic algorithms optimize the best input sequence. Just a thought.
You're asking whether did I figure out how the algorithm scale with the number of parameters in the input sequence?
No, I'm just saying you find the number, the amount of input sequence increases, that becomes a challenge in terms of running your experiments. You might want to use genetic algorithms to optimize the best input sequences to use.
Oh yeah, we did use that.
Okay.
So yeah, we did, because otherwise it wouldn't be just 90 qubit gates. Yeah.
So you were showing the gate counts and the scaling with Ed. Some of them looked like kind of weird scalings.
We're scaling, what do you mean? Okay.
Had a slide that showed,
Like non-integer scaling.
Oh, non-integer, but it's,
yeah,
what, you remember as n child lecture, when you got like n, or was a scale as 1 plus 1 over to the p, where p is the order of the product formula? I think that's where it's come from.
okay.
It's about, yeah, and the other numerics are the fit. I don't know how to explain it, probably you need to look at the proof.
No,
No,
that's it.
Yes, okay.
Yeah.
Okay,
Perfect. And then we'll take one last question in the back.
Thank you for this great talk.
thanks.
I wonder whether it's convenient to change the electric charge on the fermion in the 1+1 utility, like from the unit electric charge to like 2 units, 3 units. It's because there's a slightly more interesting symmetry structure there. That would be interesting to say the implications from simulation side. I just don't know like whether it's convenient or to change the electric charge.
Well, so what the question is whether I can change my electric charge to like 3 instead of 1 because there's more interesting dynamic in that sector. So I can't, well, okay, theoretically you can always use a highly excited charge ions, but then it is more difficult to control. Probably we shouldn't do that. So, and we probably there's some way to map the Hamiltonian of this three charges to something in the spin Hamiltonian that we can do it on our system. So I think that's, I don't know what model you're talking about, but just talk to Zora and that is possible, I think. I think Zora can make everything possible, yeah. Okay.
Great. All right, let's thank Nhung and Dominique again.